This video shows you how to build the model that we've used in our stream depletion case study. So first of all, we want to do step 1, which is open or create a new file. So we'll go to File and save our blank Anaqsim project. I'm going to call it stream depletion, and I'm going to call it steady at the moment, and the reason for that will become clear later. Next, it's good if you've got a base map to load that. So let's go to plot input, what to plot, and we'll select a base map, which I've got one here. Make the plot. And for the first time, we're probably going to have to zoom out a fair bit to find where this base map is. And then I will set the plot to the current view. So every time we plot, it should now come to this view. The second step is to define our vertical layers. So that is our domains. We go to model input, domains. We're going for a confined and unconfined one. So we're going to call it aquifer. This is a single layer model, so there's only one domain. It's unconfined. And then we've got some extra values in here. These values are based on the case study information. So that's the only domain we need. The third step is to input some horizontal boundaries and our wells. So we're going to start with the kind of external boundaries to the model. So if we go back to plot, these are the external ones. So we've got a boundary all around the outside, which is the sort of watershed boundary, and then we've got a downstream boundary. The watershed one is a no-flow boundary, so it's along the top of the catchment. We're going to digitize a polyline along this boundary. We don't need to be particularly precise, but we right-click, digitize polyline, and then we click along it. You can also have the coordinates, if you know them, in a spreadsheet and copy and paste them in later into the dialog box that this gets pasted into. I'm going to right click, and that has ended the line. If we now go to model input, line boundaries, and it's a no flow boundary, so we go for normal flux specified. I'm going to give it a label of distal boundary. It's aquifer. It's a domain boundary. We start our flux start and end is 0, so that'll be no flow. And then if you click edit coordinates, the coordinates that we digitize should be on the clipboard. So I'm going to do a paste, Control V for paste, and that's put those there. So you could have just pasted this directly from Excel. Right, if we do save, and then I'm going to make the plot, model elements only. So it's got an error because we haven't actually got a fully closed boundary yet. We didn't close the end. But if we do OK, I think this should still plot. Yeah, that's correct. So that green line is now the boundary we've just digitized. And we will close it off with the downstream boundary. So again, we are going to digitize a polyline. And now, because we've got existing points, there's a little snap to, which is good. So we'll go from there to there. And then I right clicked to kind of end the line. Model input, line boundaries, we'll go to head specified. Now the label for this is exit boundary. You can call it what you'd like to. And then domain is aquifer, it's a boundary. And our level here is 144, the downstream end. Edit, and then here again, I'm just going to paste. Okay. Let's save, and then make the plot, model elements only. Right, it now has worked out what levels there are in the model, and we haven't got any of those errors. And that's that boundary, and that's that one. So that's our external boundaries now complete. But we've got some internal boundaries to include. So this dotted line, this is a tributary, and then we've got a sort of main river coming down. We'll start with the tributary. Again, we want to digitize along it. So we'll right click, digitize polyline. And then I'm going to start from the top and click along. Get to the end, right click. Sometimes there seems to be an error, but I think that's all there. We go to line boundaries, we'll go to river. And this is tributary. The domain again is the aquifer. It's going to start at 153 and end 147. Got conductance values of 2.5 all the way along. And then the base resisting layer 151.5 and 145.5. And I've just pasted those coordinates in. If we save and go to make plot, that's now become a river. So we're going to do the same for this upper section and then for the lower section. Digitize polyline. Model inputs, line boundaries, river. Mainstream upper. Aquifer. Got slight changing conductivity here. Yeah, that's 2. And then paste those coordinates in. And then I'm going to go and digitize the last section. Now, we don't have a midpoint on this boundary, and it's quite important not to extend beyond the boundary. I'm just going to come up close and add a point in there. Do a right click to end it. Let's go back to line boundaries, river. Mainstream lower. It's important to make sure that the stage is the same where all 3 of those streams meet. So we've got 147 as the bottom of the tributary, and we've got it as the bottom of the upper section of the mainstream, and we've got the same value as the top of the lower section of the mainstream. So that should all give the same value. And I just need to paste those coordinates in there. Right, let's save. Brilliant. You could have had this lower river. If we had put a midpoint on this boundary, you could have had it snapping to that midpoint, and that would work fine. Next, we want to add a pumping well. It's about here in the model. So we right click, you can do digitize point. There we go, clicked. It has copied it to the clipboard. So you go to model input, pumping wells. It's going to be discharge specified. Let's call it a test well. There we go, we pasted it. Radius is 0.2. And for the moment, we're going to give it a discharge of 0. So that means it isn't going to do anything, but we're setting it up to create some baseline initial conditions. And then in a transient model, we will set it to pump. Let's make the plot. That's our well sitting there. So this model is going to become a transient model. And in transient models or multi-level level models, we need to include recharge nodes because they kind of help tell the model what storage there is and also sort of vertical flow information. So we're going to go to model import and they are under here area source sync. So first of all, we want to set the recharge nodes across the entire domain. So we'll go spatially variable domain. We've only got one aquifer. This is also where you can set any recharge that is happening. So we have a small top flux. We've got nothing going out the bottom, and I would want a node spacing of about 400. Now nothing's showing up on here, but if we go to plot input, what to plot, we can change what is getting plotted here. We want to include the control points. So now we'll go save, make plot. And these little crosses, they are our sort of recharge nodes. So we've got a fairly good spacing across the whole model domain. However, we are interested in particularly in what is happening around where this well is. So we're going to add a polygon around here that's got a higher density of nodes, because this is where we're expecting to have more significant groundwater flow. We will digitize a polyline, and I'm just going to go for a rough circle joining back there. And now we'll go to model input, area source sync, and this is spatially variable polygon. So we are going to call it a well zone. We don't need to set the recharge, it will take that from the wider domain one. All we want to do is increase the spacing here to 75, and add some coordinates. We'll save that, make the plot again, and here we've got a region of much higher density. We can also add in specifically around this well some extra points. So for that, we go to area source sync, and these are called well basis points. So you select your well. Doesn't like that. So let's first put in a spacing. We'll select, and now that well has appeared. We want our max node spacing to be 125, and we actually want 10 points around the circle. ID save, make plot. So here we are. I'm going to zoom in, and you can see we've got a much higher density just around the well, which will make our results more accurate in that area. We're now ready to run the simulation. So we'll click solve. That's it solved. And now we can make the plot. And nothing's turned up. That's because we need to select what we want to plot under plot input. So if we go back to here, what to plot, and let's tick contours on. Let's save that, make the plot. Here we go. So this all looks relatively sensible answers. We can see that the stream is having some impact, and the flow is generally going from upstream in the catchment down. The well, because we've got zero pumping, isn't doing anything yet. It hasn't affected those streamlines, those contours, at all. What we want to do next is we'll use these results to create initial conditions, and then we're going to make it into a transient model. So if we go to File, we want to save the locations for initial transient heads. So that's going to save a file. What that file has in it is just the locations of all of the places that the model has information to start the next set of initial conditions. So that's just the location information. We then need to go File, Write Initial Transient Heads. Click that file, the location's in. And then it will ask us for a new name. Just keep it to the standard one. And this file will actually have the kind of water levels, the groundwater levels at all of those locations. So that's our initial condition saved. If we now go, we'll save this as a transient model. And now if we go to model input, general, let's untick steady. So this becomes transient. Save that. And then the other thing we need to do for the transient is we need to add some time steps. We're going to have 2 time steps. The first is going to be 100 time units long. I think in this case, the time units are days. And we'll have 5 days in each, 5 steps in each period. And we just want them equally spaced throughout that time. Our second one, time period, is going to be, 300. We want 10 steps in that time, and again, they'll be equally spaced. So the reason we've got 2 time periods is the first one is when we're going to have the pumping on, and then the pumping is going to be switched off, and we'll be able to see the recovery. So we now need to go and change the pumping well. So we had it on 0. Instead, we want to do a discharge of -550 for the first time period, and then you put a comma, and then we want to do 0 for the second time period where we stop the pumping. So now we're going to solve. It's asking us where our initial heads are. So these are the initial conditions that we saved from the steady state model. So we'll click on that one, open, and we are now solving. Solve has completed. So let's go to make plot, and we will choose our level and time. So because it's a transient model, we now have various time steps available. So let's go towards the end of time period 1. We'll do plot. And here we have got the general sort of head contours, and you can see that there is a drawdown at the well. So if we zoom in a bit, we'll go to plot input and we'll reset the plot window. And if we plot again, it will come out a better resolution. There we go. So we've got quite a significant drawdown at the well. If we go to make plot and we choose a later time, so let's go to the end of the second time period. This is after we have stopped pumping. That drawdown has stopped at the well. And if we zoom out again, we will set the plot window to the current view and then remake the plot. You can see the contours are back to being mostly influenced just by the streams. Now, what we're actually interested in is the change in base flow to the streams. So to get that information, we can go to Analysis, Riverline Boundary Discharges, Individual Reaches, and we will write those discharges to the run log. So here we have the 3 different reaches, and we are mostly interested in the mainstream upper, and we can see how the numbers here are changing from in the first time period, they're slowly decreasing. So that means that less base flow is heading to the river. That decrease continues through till sort of about this row here. So it continues to decrease after the pumping has stopped. And then there's a bit of a delay before we start seeing the rebound in the groundwater flow.